Hello, my name is Brooke Conrardy, and I will be discussing the third stage of the coffee project, coffee roasting. Coffee roasting is a pretty well-known process. It's done in large batches by corporations as well as in single batches in homes for specialty roasts. Roasts range from being light and sometimes fruity or even chocolatey to dark and rich. The process usually requires 8 to 15 minutes of cooking time, and beans are endothermic initially, and they absorb outside heat until they reach approximately 190 degrees Celsius at their core. At this point, they become exothermic and self-heat. This is an important factor to consider when looking at changing roasts. It's done in a couple of different ways. One way that roasting can be done is drum roasting, in which a heated horizontal cylindrical drum is rotated constantly in order to ensure an even roast type. This type of roasting is very popular in large manufacturers because it offers a high level of consistency between roasts. The other way that roasting occurs is in hot air bed roasting, in which beans are placed on a screened surface which has hot air pushed between them with enough force to lift and turn the beans. While also popular, this method is also especially useful for research. A camera can be placed right here above the cooking beans, and photographic data can be collected while the roasting process is happening. Both studies that I used for my research project used this method for their papers on changing color of beans. So in Figure 1, you can see some of the trials conducted by J.A. Hernandez showing the change in gray level of coffee beans over time at different temperatures. This generally referred to the change in RGB values, although exact gray value calculations weren't specified. However, despite a lack of equations or even quantification of so-called gray levels, this paper gave important visual tools, which I decided to replicate in Figure 2. In a similar study, a man I'll refer to as Mr. Azaredo, because I can't pronounce this, determined a differential equation that should predict the changes in what he called lightness over time at a given temperature. He actually quantified lightness and calculated it by adding together the red, green, and blue color values and dividing the resulting value by 3. Using a combination of this information, I created Figure 2, which shows how coffee beans roast over time at 5 different temperatures. The code involved used Euler's method to solve the given differential equation over time and temperature. I varied the time over 800 seconds in order to capture the entire roasting process, and the temperatures vary by 800 degrees Celsius. I'll get more into this code in just a minute. So this slide shows the final stage of my project in which I created a graph of all times and temperatures possible. All beans begin at a lightness of approximately 60, which is this top color bar value, and fall in lightness while the bean cooks through. At about 100 seconds, the beans lose an outer layer, which kind of flakes away and makes the lightness go back up. So the beans will rise in lightness for a short period of time until the beans become exothermic, or as I mentioned before, self-heating. By showing the data in this way, it's easy to see why roasting is ineffective below 200 degrees Celsius, as the beans will not reach the lowest roast and will never become exothermic. Because of this, even though the outside of the bean will roast, it will be unlikely that the bean will cook completely through or attain the desired flavor profile and will be useless for brewing. This also shows why spending money to cook the beans above about 400 degrees Celsius is unnecessary. The beans will follow a similar roasting pattern at all temperatures above 400 degrees Celsius, but at extremely high temperatures, it's likely that other compounds not related to the color will burn off, disturbing the very delicate flavor profile. I'm now going to switch over to my MATLAB program and show a little bit of what I did with that. So you can, the first part of the program inserts the constants into a k value, which will be the constant of proportionality for the differential equation. And I will then change the temperature and time, as you can see here, to calculate k through both temperature and time, and then solve the differential equation numerically using Euler's. Finally, I plot 5 specific curves as well as the comprehensive curve to get what you're going to see in just a moment. When I run the program, I just automatically put in 0 degrees Celsius, and you can see this one is the first figure, which I will insert to show you these different temperatures that each one shows. And finally, here's our final graph, which I love, my 3D representation of everything, which I love because I'm actually able to see the changing color profile over time and temperature. So overall, I created this tool to be what I believe is an important visual representation of what happens when coffee roasting occurs. By rotating this, you can see a lot of different valuable things about coffee roasting. So I like this as a tool to be used in a number of different ways, whether or not you tweak it to match exactly what your roast colors would be, or to make sure that you're showing why going above 200 degrees Celsius or not being too hot is going to be necessary. Thank you.